Air Marshal Yalla Umesh, Air Vice Marshal Golani, Shri Neeraj Gupta, all the dignitaries in the audience, ladies and gentlemen. A very good morning to all of you. As you heard in my biodata, I started as a materials engineer. 30 years of my career was based on pure R&D in the materials domain. And the last 10 years, I have spent more as a techno manager. So what I'll do in my speech here is not get into the technical details of different materials, because there are myriad, I would say more than 1,000 materials which are needed for various applications in defense. But I'll try to highlight the broader challenges that we face in this domain. As my previous speakers have mentioned, materials are key enablers, whether it is systems, whether it is weapons, whether it is sensors. If you want the next or higher capabilities than what you currently possess, you have to develop materials which can give you that capability. If you are dependent on foreign countries to give you this technology, you are not going to get it. They will give you the technology only once they have used it in their systems. And when they move to the next generation technologies, when they give you the various components of technology which is needed for making your systems. So if you have any ambition of becoming Atmanirbhar and a technology leader, this is an area, I would not say this is the only area, but this is one area which the country needs to focus on. It's not that we have not been doing materials research, as my previous speakers mentioned. In DRDO, we have 3 or 4 laboratories who work specifically on materials. We have DMRL, which focuses mostly on metallic materials. We have DMSRD in Kanpur, which focuses on polymers. And we have SSPL, which focuses on electronic materials. We have HEMRL, which focuses on high energy materials, that is explosives and propellants. And there are several other laboratories which also work on materials. For example, ASL, which is our missile laboratory, has a very strong composites division. So DRDO has realized the importance of materials long back, and this is one of the thrust areas in DRDO. But I would like to point out the challenges we face. It is very easy to develop materials in a laboratory. Today, if you look at our extramural funding that we do, 40% of the funding goes for materials development in academia. A lot of new work happens in these academic institutions as well as in various DRDO labs. But very few of this get translated into industrial production. The valley of death is very strong in the materials domain. For every 100 new materials that you work on or you develop, hardly 2 or 3 get translated into industrial production. And this is true not only in the country, but globally. And that is because the properties that you get in the lab are rarely scalable when you go to larger production. In the lab, you also don't look at how that material can be manufactured, how it can be welded, how it can be machined. Those aspects are usually not looked at when you study a new material in a lab. The other challenge is the economics of translating it into industrial production. The cost or investment required to industrialize any material is very high. See, if you are working in the IT domain, you are working in developing some software, you don't need to invest much. You have to invest only in the software developers which are going to work. The hardware costs are very low. But if you want to translate any material into any production, the investment required are usually more than 1,000 crores. And in most cases, especially for materials used in defense applications, the volumes are not very high. So if you are going to invest 1,000 crores, unless your turnover is going to be 5,000 or 10,000 crores, you are not going to be able to sustain your industry. The other problem we face is that even if you translate it into production, what happens is the foreign country drops the price. So if you are able to produce, let's say, 1,000 rupees a kg, for example, a steel or a titanium alloy, the foreign country will start selling you that material at a lower cost. And the industries which use the material as their starting point would rather import it than buy it from an indigenous source. So just to give you an example, DMRL worked on making titanium sponge. India, if you see, has the third largest reserve of titanium mineral. So the ilmenite and rutile in our beach sands in Kerala, Tamil Nadu have significant fraction of ilmenite and rutile, which are the basic ores for titanium. We were selling ilmenite and rutile, so you were not getting the full value addition. So for every 100 rupees of ilmenite or rutile, if you sell it, you lose 4,000 rupees if you convert it to a titanium alloy and sell the titanium alloy. To make a titanium alloy, you need titanium sponge. We, in DMRL, this is a very challenging technology if you have to scale it. We worked on it in a lab, then converted it into a pilot plant, and then transferred this technology thanks to ISRO, which funded that plant. They funded 500 crores to set up this plant in Kerala, KMML. But since this plant was at 500 tons per annum, because the requirement in the defense sector was hardly 300 tons per annum. So the plant capacity was set up at 500 tons per annum. But if you see the plants in China, Russia, Kazakhstan, they operate at 10,000 tons per annum. Now, if you operate at 10,000 tons per annum, your costs because of scale comes down. So for this plant to compete is extremely challenging. And titanium, as you know, is a cyclical material because it has uses in commercial aircrafts, it has uses in the chemical industry. So there are times when titanium prices shoot up, and there are times when the prices dip. And this is true with most metallic materials. When the prices shoot up, the plant is competitive. But when the prices fall, this plant is not competitive. And it's been a struggle for this plant to maintain production. So although technology has been developed, since the demand for titanium alloy in the country is not as much as what it should have been, the plant is finding it very hard to survive. So this is one challenge. So even if you develop technology to sustain it, unless somebody invests and sets up a plant at a capacity where it can be globally competitive and sell to the global market, not just the Indian market, this challenge is going to remain. Let me give you another example of the steel that we developed for our naval hulls as well as for our submarine hulls. Now, the requirement is about, say, 20,000 tons per annum. This looks like a large amount, but India's steel capacity is close to 10 million tons. Now, if you say that I want to produce 20,000 tons, most steel plants say, see, this will, and the quality requirements for any defense application is significantly higher than their commercial production. So they have to stop their commercial steel production, what they do, and dedicate their plant to produce your steel, which again becomes a challenge because unless you are willing to pay a very high price, they are not willing to change over to meet your requirements. But fortunately, we have been able to find a few steel plants who have graciously agreed to do this, and hence today we are self-sufficient when it comes to naval hulls, ship hulls as well as submarine hulls. So these are some of the challenges that we face during industrialization. But the biggest challenge we have today is the material development cycle is 10 to 15 years. And if you see, the system development cycle is continuously shrinking. Today, new systems are coming in every 5 years. And in things like drones, every couple of years or every year, things are changing. So unless the material development cycle keeps pace with the system development cycle, getting any new material in is becoming greater and greater challenging. So there are attempts being made by the materials community to shorten the materials development cycle, and as has been mentioned by one of my previous speakers, people are using what is known as integrated computational materials engineering, AI/ML tools to shorten the materials development cycle. I am very hopeful that in the next 5 to 10 years, the materials community will also be able to shrink the materials cycle. The next challenge after you produce materials is to convert that material into the product form that you need. That is where manufacturing comes in. The traditional methods by which materials were made into a product was casting, forging, rolling, sheet metal forming, then joining by welding, brazing, soldering, and then machining it to the final shape. These are traditional methods which were being used. And I can say today that the manufacturing capability in the country today is excellent. We have made significant progress, and I have seen this over my career, that today our manufacturing capabilities, I would say if not the best in the world, are quite competitive. But for a typical aeronautical part, if you start from an ingot to that final part in, say, a titanium alloy, the final part is just 15% of what you started from. So you started from an ingot to that final part which you use. The wastage in materials is very high. So we necessarily also have to look at the recycling technology. That is one area where we have not focused on. It is changing, but recycling technology has to be addressed. Otherwise, the cost of your product becomes very high. The next challenge is, again, can we find a manufacturing method which is suitable for this low volume, high performance requirement? And this additive manufacturing, which has emerged in recent years, gives us this manufacturing method. Because you don't have to go through all the steps. You can make near net shape by additive manufacturing. Maybe some finishing technologies may still be required to meet your performance goals. For example, most of the surface finish in additive manufacturing is not up to the mark what is required for, say, an aero engine part. So you will have to do some finishing operations. Also, if you are interested in fatigue and creep properties, the porosity which is inherent in an additive manufacturing process has to be healed using hipping, that is hot isostatic pressing. So those technologies from traditional manufacturing may still be needed. So that is why what the future may lie is in hybrid manufacturing rather than pure additive manufacturing for defense applications. But the challenge today in additive manufacturing is that we don't have any sovereignty. As very rightly mentioned by Air Marshal Umesh, we are dependent on the powders. We get only a limited number of powders. We are dependent on the machines. Most of the additive manufacturing machines come from abroad. So if you want sovereignty and control over your process parameters, as a nation, we will have to work on making the machines on our own, doing R&D and manufacturing the powders on our own. And the final challenge in additive manufacturing, especially for aeronautical applications, is the certification. The traditional certification methods which were used for certifying materials and then the subsequent products are not suitable for additive manufacturing. We will have to evolve our additive manufacturing certification processes. I'm quite happy to tell you that in all these areas, a lot of R&D is now happening in the country, but a lot more needs to happen before we can achieve Atmanirbharta in these areas. So to conclude, what I would like to say, that we have the right ingredients in place today in the country. We need to invest more. We as a government will have to invest in at least pilot scale facilities where researchers who have come up with something in the lab cannot on their own set up these facilities. So the government has to take steps to set up these pilot facilities so that an industry is confident that the technology which is developed in the lab is scalable. And once the industry sees that it's working at a pilot scale, then they can take it forward and invest. We have to look at the global market. We can't afford to just look at the Indian market. And the final point which I missed is we have to look at the critical raw materials which go into making materials. See, today we have the magnet technology, but we don't have the rare earth metals. China controls 90% of the rare earth metals. And the heavy rare earths which are needed in the neodymium iron boron magnets, China has 99% dominance. So we have to look at tungsten. Today, we don't have any tungsten in the country to make tungsten heavy alloy. We have the technology to make tungsten heavy alloy, but our dependence on tungsten is still very high. It's not that these resources are not available in the country. We have resources of tungsten in the country. We have resources of rare earths in the country. But we have not paid enough attention to the extraction technologies. We have not paid enough attention on exploring our country to see where these resources are. So you have to look at this holistically if you have to make a mark going ahead. I'm sure that with the increased focus of the government on Atmanirbharta, all these issues will be addressed. So I'm very glad and I congratulate CAPS for organizing this workshop, and I'm sure the deliberations that you will have will lead to some roadmap which you can propose for the government to take it forward. So my best wishes to all of you, and have fruitful discussions during this seminar. Thank you.